Section 9. Control of stray current interference. 9.1 Introduction. This section outlines practices for detecting and managing electrical interference arising from stray currents. 9.1.1 Stray current interference is any discernible electrical disturbance on a structure originating from a stray current. These currents can be static or dynamic. 9.1.2 Static stray current is defined by its consistent magnitude, direction, and location on a pipeline. It is frequently seen at pipeline intersections and near external impressed current anode beds not electrically connected to the pipeline. 9.1.3 Dynamic stray current is characterized by fluctuating magnitude, direction, and location on a pipeline. It is often observed near AC or DC transit systems, high voltage AC or DC power lines, or through naturally occurring geomagnetically telluric induced currents. 9.1.4 When conducting stray current testing, all reasonable attempts should be made to inform potentially affected parties. Testing protocols, schedules, and mitigation standards should be agreed upon before testing. Where feasible, notification should be disseminated through local corrosion control coordinating committees. 9.2 Typical sources of stray current. 9.2.1 Direct current. 9.2.1.1 Internal and external cathodic protection (CP) sources. 9.2.1.2 DC-powered railway and transit systems. 9.2.1.3 Mine transportation systems and pumps. 9.2.1.4 Welding equipment. 9.2.1.5 Facilities employing grounded DC induction apparatus. 9.2.1.6 High voltage direct current HVDC power systems. And 9.2.1.7 Other DC power systems. 9.2.2 Alternating current. 9.2.2.1 AC power transmission systems and AC powered railway systems. 9.2.3 Telluric current, naturally occurring geomagnetic earth currents. 9.3 New construction elevated stray current density at discharge points on a pipeline can lead to accelerated pitting. For new pipeline projects, vulnerability to stray current must be evaluated before and during construction. Any necessary mitigation measures should be engineered and implemented concurrently with pipeline installation and monitored for efficacy. 9.3.1 For new construction, the following steps are recommended. 9.3.1.1 Before construction, endeavors to identify and plan for the mitigation of foreseen stray currents should be undertaken. 9.3.1.2 During construction of the mitigation system, as per the plan, testing should persist to ascertain effectiveness. 9.3.1.3 After construction, a commissioning survey should be performed, and the efficacy of the implemented mitigation should be validated. Identified shortcomings should be rectified as needed. 9.4 Personnel safety. 9.4.1 Physiological effects of DC or AC currents. DC or AC currents can be detrimental to personnel if contact is made with a metallic structure influenced by stray current. The physiological impacts are contingent on the magnitude, the path through the body, and the duration of current exposure. These effects may encompass minor nerve sensation, muscle contractions, cardiac arrest, burns to tissues and organs, temporary paralysis, and damage to the nervous system, and fatality. 9.4.2 Protecting personnel from electrical shock. Hazard. 9.4.2.1 Engineering controls. CP equipment should be designed and installed to preclude accidental contact by personnel with energized components under the influence of stray current. 9.4.2.2 Personal protective equipment, PPE. Where engineering controls are not viable, PPE may be necessary, including but not limited to appropriately rated and sized rubber gloves and footwear. 9.5 DC interference. 9.5.1 Effects of DC stray. Current interference. 9.5.1.1 DC stray current corrosion on underground or submerged metallic piping systems is distinct from other corrosion causes, as the current responsible for the corrosion originates from a source external to the affected structure. The stray current is drawn onto the pipeline where it is subjected to an external anodic voltage gradient. If no metallic pathway exists between the external structure and the affected pipeline, the current will flow from the pipeline into the electrolyte, returning to the interfering structure. 9.5.1.2. The stray current magnitude in the metallic piping system is a function of the resistance of the stray current path and the driving voltage between the structures. 9.5.1.3. A metallic piping system with a positive potential relative to the surrounding earth discharges current into the earth, potentially causing corrosion. A metallic piping system with a negative potential relative to the surrounding earth attracts current from the earth. 9.5.1.4 Effects of DC stray. Current at area of current pickup. 9.5.1.4.1. At the current pickup location, a negative shift will induce cathodic polarization. 9.5.1.4.2. If the metallic piping system is composed of an amphoteric metal, like aluminum, lead, or zinc, the elevated pH generated at the structure-electrolyte interface due to the reduction reaction can lead to corrosion. 9.5.1.4.3. If the affected piping system is prone to hydrogen embrittlement, such as pre-stressed concrete cylinder pipe or high-strength steels, stray current at the pickup point may result in excessive cathodic polarization, potentially causing damage. 9.5.1.5 Effects of DC stray current along the piping system. Stray current within a metallic piping system typically does not cause damage between the stray current pickup and discharge points unless high resistance joints or an electrical discontinuity are present. 9.5.1.6 Effects of DC stray current at the area of current discharge. When DC current transitions from metallic piping to the electrolyte, it discharges through an oxidation reaction. This oxidation reaction leads to metal loss at the pipe-to-electrolyte interface. 9.5.2 Detection of DC stray currents. 9.5.2 1. Detection of static DC stray currents. During external corrosion control surveys, personnel should be vigilant for electrical or physical signs that could suggest static stray current from an external source, such as 9.5.2.1.1 pipe-to-electrolyte potential variations on the affected structure, which can be seen at both current pickup and discharge locations. 9.5.2.1.2 Changes in the pipeline current magnitude or direction, which can be observed at current measurement points. 9.5.2.1.3 Localized pitting near an external structure with impressed current CP, which can be detected during pipe inspections or inline inspection (ILI) runs, and 9.5.2.1.4 Damage to external coatings in a localized zone near an anode bed or any other stray current source, which can be identified through coating surveys such as direct current voltage gradient (DCVG) or alternating current voltage gradient (ACVG). 9.5.2.2 Detection of dynamic DC stray currents. During external corrosion control surveys, personnel should watch for electrical or physical indications that could point to dynamic stray current from an external source, such as 9.5.2.2.1 pipe-to-electrolyte potential fluctuations on the affected piping system, which can be observed at a test point. 9.5.2.2.2 Fluctuations in the current magnitude or direction, which can be seen at current measurement locations. 9.5.2.2.3 Localized pitting, and 9.5.2.2.4 Damage to external coatings near an external structure like a DC transit system, HVDC power lines, welding facilities, or similar installations that utilize DC induction equipment, which can be detected during pipe inspections, DCVG or ACVG surveys, or ILI runs. 9.5.3 Measurement of DC stray current interference. In many instances, particularly with dynamic stray current interference, multiple stray current sources exist. The following are typical test methods employed to assess each potential stray current source. 9.5.3 1. Measurement and correlation of structure to electrolyte potentials with data loggers on both interfering structures and affected piping systems to pinpoint the source as and locations of stray current pickup and discharge, and 9.5.3.2 Measurement and correlation of current with data loggers or current mapping tools on both interfering structures and affected piping systems to identify the source S and magnitude of stray current pickup and discharge. 9.5.4 Severity of DC stray current interference. Unlike other naturally occurring corrosion mechanisms, where the corrosion rate is limited by the chemical reaction thermodynamics, the corrosion rate from DC stray current can be considerably more aggressive. The severity of DC stray current hinges on several factors: 9.5.4.1 Distance and routing of the interfering and affected structures, 9.5.4.2 Magnitude, duration, and current density, 9.5.4.3 Electrolyte resistivity, and 9.5.4.5 Presence and location of electrical discontinuities along the stray current path on the pipeline. 9.5.5 Mitigation of DC stray current. CP current can be applied to the affected piping systems at points where the interfering current is being discharged. The CP current source may be galvanic anodes or impressed current. For this method to be effective, the driving voltage of the CP current source must exceed the driving voltage of the stray current. Other potential options for mitigating DC stray current between two pipelines include 9.5.5.1 Installing galvanic anodes on the affected pipeline at the stray current discharge point as a sacrificial discharge path. 9.5.5.2 Installing a direct or resistance bond between the affected pipeline and the interfering structure. 9.5.5.3 Reducing the output of the interfering source. 9.5.5.4 Removing or relocating the interfering source. 9.5.5.5 Applying a coating to the affected pipeline in the stray current pickup zone or to the interfering structure where it picks up the returning stray current. 9.5.5. 6. Burying an electrical shield parallel to the affected structure at the stray current pickup zone. 9.5.5.7. Installing electrical isolation fittings in the affected structure. And 9.5.5.8. If the stray current originates from a DC-powered transit system, the following techniques can be employed. 9.5.5.8.1. Isolate the running rails from ground to minimize DC stray current leakage. 9.5.5.8.2. Install, modify, or upgrade cathodic protection on the affected piping. 9.5.5.8.3. Installing galvanic anodes on the affected pipeline at the stray current discharge point as a sacrificial discharge path. 9.5.5.8.4. Installing unidirectional control devices such as diodes, forced drainage bonds, or reverse current switches may be necessary to prevent current flow reversal. And 9.5.5.8.5. In certain situations, such as rail transit with ungrounded DC traction power distribution systems, bonds can significantly reduce the transit system's resistance to earth, often with a noticeable rise in overall stray earth current levels. In these circumstances, it is crucial to evaluate the overall impact of the bond against its benefit in mitigating stray current on a specific structure. 9.6 AC interference. 9.6.1 Modes of AC interference at power frequencies. AC interference at power frequencies manifests in three modes: 9.6.1.1 capacitive coupling, 9.6.1.2 inductive coupling, and 9.6.1.3 resistive coupling, electrolytic. 9.6.2 Effects and severity of AC interference. The effects and severity of AC interference are contingent on the mode of alternating current. For inductive and resistive coupling, the effects include 9.6.2.1 corrosion, 9.6.2.2 coating damage, 9.6.2.3 pipeline damage from fault conditions, 9.6.2.4 damage to CP equipment, 9.6.2.5 personnel injury, and 9.6.2.6 welding challenges. 9.6.3 For capacitive coupling, the effect is the creation of high voltage differentials between an isolated pipe segment and the ground, but with minimal current generation. Consequently, it does not induce corrosion or present an electrical shock hazard. However, it can pose a fire hazard if flammable materials are nearby and may create a personnel safety risk. 9.6.4 AC corrosion risk is influenced by certain pipeline and power line characteristics. The primary risk factors for inductive and resistive conducting modes can be found in Table 2, not provided. 9.7 Telluric current interference. Cathodic depolarization to potentials less negative than the potential criterion can occur depending on the magnitude and duration of telluric activity, which can fluctuate significantly over short or long periods. The pipeline-induced voltage versus distance profile is somewhat analogous to power line AC induction. 9.7.1.2 Measurement Errors. Telluric current activity introduces an additional voltage drop in the earth, impacting the accurate measurement of pipeline polarized potentials. Measuring a precise polarized potential in the presence of an uninterrupted stray current may necessitate specific measurement techniques. 9.7.1.3 CP Transformer Rectifiers. An impressed current transformer rectifier will transmit a telluric current through the rectifying element to its anode bed if the telluric current is in a discharge cycle. This is undesirable because an increase, rather than a decrease, in the transformer rectifier output would be preferable during a telluric current discharge. Therefore, an automatically controlled transformer rectifier should not be operated in constant current mode when the pipeline is exposed to telluric current activity. 9.7.2 Corrosive effects of telluric currents can be mitigated by galvanic anodes or impressed current cathodic protection systems.